afternoon, everyone. Welcome to yet another lecture on the course titled Artificial Intelligence in Industrial Management Engineering. I am Dr. Deepa Philip and I am from IIT Kanpur, and this course is offered as package as part of the NPTEL MOOCs content created from IIT Kanpur. Along with me, Dr. Prabhar Pratap Singh is teaching this course as well. And we are in week 4 and we have been looking into various aspects of searching, the importance of search algorithms in AI domain and why they are significant, and we also saw why sorting is also important for searching and how it actually makes the searching process easy. And we have also seen simple search, and we also saw about the way it is classified like heuristics and etc. So, now today we have just in the previous slide, if you go behind, what we have gone is we have seen how to go through a full search tree. And today now we will move to what you call as when you change the goal, because we talked, let us now talk about the instead of reaching a goal vertex, now the goal is to visit all vertices of the graph. So, we will start with the same network as we discussed earlier. This is network A, we have B, A to B, that is 3 units, then we have C, node C, from B to C, that is 2 units, and C to A, it is 2 units, and then there is B, C, D, that is about 3 units, D to E, that is 4 units, and then there is F, E to F is 4 units, and B to F there is 9 units. This is the network that we have taken earlier. So, and if you look into it, the previous definition, we had definitions of what we call as states, at which node you are. Okay. Now, with this problem, visiting all vertices of the graph, the first thing we need is we need a different definition of the state, different definition of a state. We need a different definition of a state. Okay. So, what should be that definition? What would it be? Okay. What would it be? It is, we have to say, currently at A, also visited B, C already. Okay. So, here is one example. You can say currently at A also visited B and C already. That means, currently I am here, but what I have done is I already completed this, visited B and C and back here. So, this is what this state what we talked about. Okay. The disadvantage of this is very large number of states compared to the previous thing. This will have a very large number of states. Okay. In this case is what will happen is how many states will be there? There will be n states, and what will happen is you have to visit everything, and you can think about it as times 2 to the power of n minus 1. This is, and find out how. Your job is to find out how did I reach this number. Now, you can do this in the form of a graph, okay, but the question is how will the search tree look like? Okay. So, this is the next big question for us, is how will the search tree will look like. So, let us try to do that expansion of the search tree. Okay. So, you remember the previous state we have seen that the state tree is like this, right. So, now let us see how do we do that. As usual, we are starting with the first node, which is state equals A. Okay. A is where you are, and we also give the null set. That means, we have not visited anything and the cost is equal to 0. So, this is the example of you starting from here. Okay. this is the start, okay, and the logic is that visit all nodes, that is the stop point here. So, we are starting at A, that means we are at A, but we have not visited anything else. Now, from here if you look at the network, we have two options, we can go to B or we can go to D. Okay. So, then we will have 1, 2. Okay. So, this will be the state equal to you have visited B, we are at B, but your set is A, that means you already completed A, okay. And the cost is equal to the cost of this travel is, since if you look at backwards, it is A to B will be 3. Okay. So, the cost is equal to 3. In this case, you would have visited the D and the cost is also 3. So, that is what we will be doing here. State is equal to D, but the set is A, that means you already visited A and cost is equal to 3. Okay. You have seen that. Now, you are at state B. Okay. So, when you are at state B, you are now here. From B, you can go to C or you can go to F. Okay. Those are the two options. Okay. So, how do we do that? So, we can go to two options. So, one is state is equal to, as I said, C, but the set will have A comma B, which means you already visited A and B, and the cost in this regard is B to C is 2. So, you add that. So, cost is equal to 3 plus 2, which is equal to 5. Okay. So, you are not at state C. The other one is state equal to F, okay, the already visited A comma B, okay, and the cost is equal to it is 3 plus 9, which is 12. Okay. All right. So, this is the second part. So, now if you go back, you can see that at B you can either go to C, it is this way, or you can go to F, right. Now, if you look at C, then the only option in front of you is go to A, right, whereas in the case of F you do not have any place else to go. So, that means if you look into this, in F you cannot go beyond this, there is nothing. Okay. And below B you have what you call as, you can visit A again. Okay. State is equal to A, but the other list is A, B, C. Okay. That means you have already visited, okay, A, B and C, you have already been there in A once. So, some people also do this as the other way around, but the cost here is equal to, already the cost was 5, okay, 5 plus, and what would that be? This is the 2, 5 plus 2, 7, okay, 5 plus 2, which is equal to the cost will be 7, right. So, you do not need to do anything beneath this, because this is done, you cannot go anywhere further. And when you reach D, let us look what happens when you reach D. In D, there is only one option in front of you, you can go to E. Okay. So, D to E, which is the cost of 4. So, D we say state equal to E, comma, you are already visited A and D, and cost is equal to 3 plus 4, that is 7. Okay. So, that is one aspect. Now, when you look at E, from E you can go to F, okay, and the cost is also 4. Okay. So, now from E you are going to F, state equal to F, okay, the A, D and E you already completed. Okay. Cost is equal to 7 plus 4, which is equal to 11. And then after this you cannot go anywhere, because when you reach F there is no option in front of you. Okay. There is nothing to go beyond that. Okay. Now, what happens? Okay. You have now what to think about it as, you have reached here. Okay. Below this, now you have to go back again, the two things will happen, which is state equals, so it will be B, okay, but you have visited A, B, C, okay, you have completed A, B, C and you are going back to again, and the one way to distinguish this is this cost is equal to 7 plus 3 which is 10, and this case is state equal to D, okay, and the other case is A, B, C, you already visited A, B, C, cost is equal to 10. Okay. So, now what you can do is this will expand beneath this as the previous stage. So, you can see how this tree expands. Okay. So, while the main difference in this case which I want to highlight as part of it is the main difference is these states. Okay. If you look into the way these we have identified the states, okay, all these states, that we have to ensure visit of all vertices on graph. Okay. That is the plan here. So, now let us talk about the key concepts in search, okay, some of the key concepts in search. So, the first thing is, first one that we want to talk about is set of states, okay, set of states, the keyword is states that we can be in. Okay. This is the first concept. Okay. So, this includes the initial states, initial state and goal states, okay, or equivalently a goal test. Now, that is the first part. So, then second key concept is for every state, okay, a set of actions we can take, okay, and in this each action will result in a new state, results in a new state. Okay. That is the first thing, each action will result in a new state. The second thing is typically defined by successor function. Okay. We will talk about it, what it is, successor function, right. So, and I will write about what it is. So, for each state first we have to so the initial key concept is for set of states that we can be in. This includes the initial state and the goal states. Then for every state a set of actions we can take, and each action results in a new state, and each one of them is typically defined by a successor function. And what is a successor function? Given a state produces all states that can be reached from this, okay. If you given a state produces all states that you can reach from it, that is the successor function, right. Now, the third one, what we call as cost function, that determines the cost function determines the cost of each action, okay, or path. And what is path? Path is a sequence of actions. So, what it does is the cost function determines the cost of each action, or it can be the cost of the path. So, previously if you think about it, the cost that you see here, this is the cost of the path, Okay. All right. Whereas, so it's like how much it costed you to reach there. So, the next one, then the last point is, the last important fourth part is solution. Okay. Solution is path from initial state to a goal state. Initial state to a goal state, that is the path. Okay. So, then these are the four major things. Then one more thing comes out of is the optimal solution. We know the solution, okay, but what is an optimal solution? That is the solution with minimal cost. Minimal cost. Okay. So, the path from the initial state to the goal state is what we call as a solution, and whichever the solution which has the minimal cost, that is called as the optimal solution. Right. So, now let us look at another example, what we call it as an 8 puzzle, okay, and just this is intended to show how the tree expands. So, let us say the starting point of the puzzle is like this, okay, and what we have is 1, 2, 3, 8, 4, 7, 6, 5. Okay. This is the initial state. Okay. And now, one, 2, 3, 4, 5, 6, 7, 8. This is the goal state. Think about it like a Rubik's cube. You start from here, okay, start here and end here. That is the idea here. Okay. So, how do you do that? Okay. So, this is the beginning. So, let us expand this. Okay. Let us try to begin this, the fragment of this 8 puzzle. I am not going to draw the entire thing, but let us start with this point. Okay. So, you have 1, 2, 3, 8, 4, 7, 6, 5. Okay. This is the initial one. Okay. Now, from here what all you can do? You can do is you can move the 2 below. So, there are 4 possibilities. One is, okay, okay. So, that is 1, 3, 8, 4, 7, 6, 5. So, the first thing we can do is you can move the 2 below. So, the 2 will come here. Okay. So, this is the first thing that we can do, the 2 can move below. Okay. So, the second thing we can do is this 4 can move to next to 8. So, the second one is, second one is like this, 1, 2, 3, 8, 4, 7, 6, 5. So, in this case the 4 has moved close to the 8. Then the third one is, the 6 can move upwards, 1, 2, 3, 8, 6, 4, 7, 5. Okay. This is the third, and then the last one is, okay, what you can do is you can move the 8 to the right side. So, it is 1, 2, 3, 8, 4, 7, 6, 5. Okay. These are the 4 next states coming out of it, right. Now, from here what can we do? So, another example or another way of going down out of this is, in this one you can move 1 to this side. If you move 2 upwards, you will go back to the same one. So, you will not do that. You can move 1 this way or you can move 3 this way. So, from here you have only two options in front of you. Okay. So, the first puzzle is it is 1 3 8 2 4 7 6 5. In this case it will be okay 1 3 8 2 4 7 6 5 like this. Okay. So, two options underneath it, right. Similarly, and you if you move the other way around, then it will go back to the initial state. Okay. Same way, under this you will have two different things. Okay. I am just not drawing everything, I am just doing only a small portion of it. Okay. Just two more, and then we will you can expand the rest of it. Okay. So, what will happen in this case? We can move the 3 below to 5, or we can move the 3. So, you can have 1 2 8 4 3 7 6 5, or you can have 1 2 3 8 4 5 7 6. Okay. That is the other option. So, like this you can keep on expanding underneath them, and each one of them there will be now below this. If I draw that, okay, I am just going to complete that so that you have an idea of what we are talking about, which in this case what you can do is you can now the next only option out of this is move the 8 upwards, otherwise it will go back to the previous state. So, this will be something like it will be 8 1 3 2 4 7 6 5. Okay. And then now from here you can branch, you can move the two other ones which we want go to the other side. So, like this. Okay. Now, you can branch bigger out of this. Same way, in this case if you draw this, it will become 1 3 4 8 2 7 6 5, and then from here you can branch out more ones. So, like this each one of them will have their own states underneath it, and then you can proceed accordingly. So, this kind of a, and if you imagine elaborating this whole thing until we reach this goal state. Okay. How do we reach here? We can see this tree, this will not be sufficient, it will be a very large system. Okay. So, now I will leave the rest of the work for you guys to go through this. Okay. So, now let us talk about something called uninformed search. Okay. So, uninformed search, the main point, the first point is that given a state, if you are given a state, okay, we only know whether it is a goal state or not. Okay. If it is a goal state, we know, or is it not a goal state, that is the only thing we know, right. Now, second one is cannot say, or we cannot say what one non-goal state looks better than the other one, better than another non-goal state. Okay. So, the critical is we cannot say whether one non-goal state better than the another non-goal state, that we cannot say that. Okay. Third one, can only traverse state space blindly in hope of somehow hitting a goal state at some point. So, the idea is that what you can do is you can only traverse the state space blindly. It is like closing your eyes without having any other information. You are traversing the state space blindly, and what you are doing is you are hoping, hoping that somehow you will hit a goal state at some point. Okay. The goal state you will hit at some point, that is the hope at this point, also known as the blind search, also known as blind search, because you do not know where you are and where you are going to. Okay. But okay, key point is blind doesn't imply unsystematic. Okay. We are not implying unsystematic as part of this. Okay. It's blind, that means you are traversing blindly, you are hoping to hit a goal state, but it is still systematic. So, one of the first ones we talk about at this point is the breadth first search. Okay. And let us quickly see what is a breadth first search. So, the idea is that you have a node, you expand in this, and then you expand these levels, okay. And then after that you will expand like this, right, like this. Okay. You are expanding the, at each level expand breadthifies. Okay. So, let us talk about some of the important properties of the breadth first search. Okay. Important properties of breadth first. So, the first main property is, or first main aspects is, nodes are expanded. Nodes are expanded in the same order, in which they are generated. They are generated. We are expanding the nodes. The nodes are expanded in the same order in which they are generating. As you generate, they are the generating. So, the idea is that fringe, okay, we will talk about what is fringe in a minute. Fringe can be maintained, fringe can be maintained as a first in first out, that is FIFO. Okay. The first in first out Q. Okay. So, the fringe can be maintained. So, what is fringe? Okay. Now, this word fringe, it is equal to a set of nodes generated but not expanded. Okay. It is a set of nodes that are generated, but you are not expanded. The key word is not expanded. Okay. Not expanded. So, that is a fringe. So, the fringe, the nodes that you generate for the next level, you can maintain it as a FIFO, first in first out Q, okay, but it will not be expanded. Now, second one is breadth first search, BFS, is complete. Okay. This implies that if a solution exists, one will be found. So, if there is a solution existing of the problem, if you have a solution exist, then it will be found, that is called complete. Okay. Then BFS finds, the breadth first search finds a shallowest solution, Okay. The solution is a shallowest solution. Okay. This is, the key word is not necessarily an optimal solution. The breadth first searches, the most important aspect is it is not necessarily an optimal solution. What is an optimal solution? I think you remember what I mentioned, the lowest cost or minimal cost. Okay. So, it need not be the lowest optimal solution, but it will find the shallowest solution. Then next one is if every node has B successors, okay. This is known as branching factor, okay. And first solution is at depth D, okay. Then fringe size will be at least b to the power of d, okay, b to the power of d at some point of time, at some point. So, if there are b successors for each node or the branching factor, okay, in this previous example the b here is 2, the branching factor is 2. Okay. So, if there are b successors known as the branching factor and the first solution is at depth d, okay, and third level, fourth level, then at least you have b to d, the fringe size will be at least b to d at some point of time. Okay. So, this implies what? This much space obviously and time required. You require that much of space and time. So, you can see that it is a very simple algorithm and it can be maintained as a FIFO, the fringe can be maintained as a FIFO, and we know what is a fringe, it is nodes that are generated and not expanded. Okay. And it also finds a shallower solution, which is the solution at the lowest level, but it need not be the optimal solution, and we also saw how much of space requirement is also there. So, this is an example of one blind search that we talked about, okay, and how we will now see in the later another examples of blind search, and then we will try to see how to add some information into the blind search, so that it doesn't have to go do that much of blindness. So, thank you for your patient hearing. We will discuss more in the next class. Thank you.